Now let's find out the transfer characteristics of differential amplifier. Transfer characteristics. Let's find out the transfer characteristics of differential amplifier. Now let's find out the transfer characteristics of differential amplifier. So as you already know, that is our differential amplifier. The base of the Q1 is connected to voltage input voltage V1. Base of the Q2 connected to V2. Collector currents are IC1 and IC2. We'll assume both transistors are identical, and we can write the current equation, collector current equation. The collector current equation IC1 is equal to alpha times IES e to the power VBE 1 by VT. So IC1 is equal to alpha times IES e to the power VBE by VT, and IC2 is equal to alpha times IES e to the power VBE2 by VT. Now this in this expressions, actually this IES are the reverse saturation current of the base emitter junction. So IES reverse saturation current of base junction. So IES is the reverse saturation current of base emitter junction. So as you know, collector currents are created due to the forward bias of the base emitter junction. So base emitter junction reverse saturation current is IES. Base emitter junction potential is VBE1, and so that IES e to the power VBE1 by VT is the emitter current. So that part is the emitter current. So that part is the emitter current. Alpha times the emitter current is the collector current. Now VT is the thermal voltage. VT is thermal voltage which is KT by Q. Q is the charge of the electron. K is Boltzmann's constant. T is the absolute temperature in Kelvin. Now if I take the ratio of the two currents, that is IC1 by IC2 equals, so this alpha times IES will cancel out, and remaining part will be e to the power, that is EXP VBE1 minus VBE2 by VT. Now if I apply KVL through this branch, so if I redraw this, it can be, so that is your V1 that is connected to base, so as you can see, I have redrawn this whole circuit, and you have plus minus VB1 and that potential is plus minus VB2. So in this circuit, if I apply KVL, so that will be our loop. So that will be our loop. Actually, these grounds are shorted. So if I apply KVL through this branch, so in this case, we can write the KVL loop equation as V1 minus VB1 plus VB2 minus V2 equals 0. So here I am assuming that current is outward from the positive terminal, and that is plus. So in this case V1, and current is flowing into the plus terminal, that is minus VB2. So that's how I'm taking this. So as a result, I can write that VBE1 minus VBE2 equals V1 minus V2. So if I replace VBE1 minus VBE2 in this expression, the reason we are doing this because VBE1 and VBE2 are dependent on the transistors, whereas V1 and V2 are our input signals, which we can control from externally. So that's why we are replacing V1 this VB1 minus VB2 by this expression. So your ratio will be IC1 by IC2 equals e to the power V1 minus V2 by Vt. So if I consider that difference V1 minus V2 is Vd, so if I consider V1 minus V2 equal to Vd, so then this expression will become IC1 by IC2 equals e to the power Vd by Vt.